So, this is a simple setup for electron diffraction. So, this is basically cathode ray tube, cathode ray CRO tube, okay. And with this CRO tube, this spherical, this ball kind of ball, this is basically whole system is in vacuum. Okay. So, this one can think of that, okay, it is a screen. Okay. So, in CRO cathode oscilloscope, the same types of tubes are used. Okay. So, electron beams are coming and falling on the screen. So, here this part, white part we will use as a screen. So, here so lot of this is the power supply, you know, in CRT cathode ray tube one has to apply it is a kilovolt to accelerate the electron. Okay. So, in CRT what is there? You will have, as I explained, that you will have filament and then a cathode. Okay. So, negative voltage is given to the cathode. Okay. So, from there electron will emit and then we will have some arrangement, basically p acceleration etcetera, some arrangements are there. Okay. So, basically what I will I should main part is that filament, then cathode, then anode. Okay. So, positive voltage with respect to the cathode. So, electron will be accelerated, then focusing arrangement. Okay. So, these whole things you can see here, basically this is the, here basically you have a filament as well as I think yes. So, and cathode I think is, you can see inside this one cathode, then you will have a anode, then you will have a focusing one, next one focusing one, and this one on the top, there basically we have kept this that crystal, graphite crystal. From here I can see this, yes, some crystals is there. So, these are the compact, it is a compact equipment for electron diffraction. Although its hand is small one, but it has a lot of this, I think these are nothing but the CRT cathode ray tube, and then in CRO we use the deflection plate, okay, vertical and horizontal two sets of deflection plate to shift the electron beam in x and y direction. Okay. So, then it will be CRO, cathode oscilloscope, but here we are not using this deflecting screen, but we are using graphite, polycrystalline graphite material. Okay. So, basically we are using grating electron beam, we are using grating here polycrystalline graphite. So, it is here, just here. Okay. So, it is on the surface, this crystal is basically kept on the surface of this sphere. Okay. So, radius, and this is the screen. So, radius of this, diameter of this sphere is, diameter of this sphere is basically the capital L, as I told, length of the screen from the sample. Okay. So, that will be L. So, this I think this is supplied one, we do not need to measure, because it will be very serious issue to measure this one, because one has to be very cautious during doing experiment, because these are made of glass. Okay. So, so this power supply, if I switch on, Now, this lot of connections are going. So, this connection basically is connection for filament current, and then for cathode power, then anode power, then for focusing for that power. Okay. Electrostatic lens basically is used for focusing. Okay. So, here it is accelerating voltage, it is 0. Now, if I apply voltage, okay, apply voltage, and other I think it is when I will change other parameter, or what will be the filament current, what will be the cathode voltage, what will be the focusing for electrostatic lens for focusing, there also we need some power. So, that all are fixed. So, here only I will change the anode voltage. So, it is in kilovolt, the reading I will get from here. Okay. So, now it is 0 volt, now it is 0 volt. Okay. Now, I am applying voltage, and if you look here, you should be able to see, first we will see the electron beam, just you can see here electron beam. Okay. So, it is the 1.4 volt, see electron beam. Okay. So, now if I increase the anode voltage, you see if we increase the anode voltage. So, I am seeing, I think I will switch off light, just see here it is, I think I can use the torch for showing the current. Yes, it is the 3 volt, it is the 3 kilovolt. For 3 kilovolt, when I am applying 3 kilovolt, now clearly I can see the two ring, one is here and another is this one. Okay. So, at this, so what I will do, I will basically, so what I have to do, I have to measure basically the radius of this, I have to measure the radius of this ring 1 and ring 2. So, ring 1 for a D1 say plane interplanar distance D1, okay, say 1 for a particular one plane, this is for another plane, its planar spacing will be different, say D2. Now, for this, so I have to measure the basically I will measure diameter and half of it will be radius. Okay. I will use the slide calipers, I will measure the internal, that because it is not very sharp ring. So, it is a broad ring. Okay. So, I will measure the diameter of the inside, inner diameter and outer diameter. I will measure inner diameter and outer diameter using the slide calipers. So, his Vernier constant is basically for this 0.1 millimeters, 0.1 millimeter. So, 0.01 centimeter. Okay. Yes, 1 by 10. So, I think these are very elementary. I have discussed this one in experimental physics 1, how to find out the Vernier constant. Okay. So, I will use for this first ring whatever the diameter, outer diameter and inner diameter I have to measure. Okay. For second ring also same way I have to measure. Now, this is just C table, experimental data. Okay. So, Vernier constant I have to find out because I need slide calipers. Now, data for D1 spacing means for a particular one for a particular plane, Okay, for a particular plane. So, D1 and for D2, data for D2 spacing and data for D1 spacing, because here we are seeing two ring, that is for two planes. So, two interplanar spacing will get, one is D1, another is D2, fine. Now, applied voltage V in kilovolt. So, I will write, I have applied kilovolt, that is I will write 3 kilovolt. Okay. I will write 3 kilovolt. Okay. For this 3 kilovolt, I will get this two ring, and I will measure the inner diameter and outer diameter, as I told, because this is the this ring have thickness. Okay. It is not very sharp ring, it has thickness. So, inner diameter, outer diameter, and then mean diameter, we will take mean average of these two diameters, average one. Okay. So, from there half of it will be the radius r, small r. Okay. So, for 3 volt, then I will change, and the same I have not shown here this table, but same table you have to make, and for this 3 kilovolt you measure the diameter of the second ring. Okay. Now, I will go to the next energy, say it is so next say 3.5 we can go. Now, it is 3.5, then you can same way for 3.5 you measure. Now, I am going to 4 kilovolt. Okay. Now, I am going to 4 kilovolt, is becoming more prominent. Okay. It is becoming more prominent, fine, it is nice. So, same way you use this for this 4 kilovolt, you measure the inner diameter, outer diameter, then average diameter you will find out. So, from there you will get the radius. So, this is the radius of the first ring, ring 1, and radius of the ring 2 for 4 kilovolt, means for a particular wavelength lambda corresponding 4 kilovolt. Okay. So, then I will go 4.5, then let me go 4.5, then 5. Here I am at the 5. Okay. It is the more prominent, you see, it looks better, but you can see this diameter is reducing, decreasing with increasing the kilovolt, increasing the accelerating voltage. If accelerating voltage increase, lambda will be small. Okay. If lambda is small, 2d sin theta equal to lambda, if lambda small, then for a particular d, theta will be small. Okay. So, cone, whatever cone we are getting, I explained. So, that cone angle, that cone angle will be smaller. Okay. So, higher the energy, energy means higher the accelerating voltage, smaller the wavelength, theta will be smaller. Okay. So, the circle will be radius, diameter of the circle or radius of the circle of the ring will be smaller. So, that is why it becoming smaller. So, one should measure this. Just I am now decreasing, and you can check that now I am decreasing, the you see diameter of the ring is increasing, you see diameter of the ring is increasing. Okay. So, that means energy is decreasing of the electron beam. So, wavelength is becoming higher. So, theta will be higher. Okay. So, if theta is higher, tan 2 theta equal to basically r by L, okay, small r by L. Okay. So, it is going out, as if this is going out, it is very small energy, that it is a diameter of this ring is so big. So, it is not in this range. Okay. So, if I increase again, it will come back. Okay. So, just for different energy we will measure. Okay. So, let me just keep at lower a. So, so this way you take the reading for 3.5, 3.4.0, 4.5, 5. So, 5 reading you can take. 2 yes 5 reading you will get this for 5 wavelength you are getting the basically you are getting the diameter or radius of ring 1 and ring 2. So, this corresponds to different wavelength, this corresponds to different wavelength. Okay. So, that means data for graph anode voltage in kilovolt. So, corresponding wavelength you can calculate from this relation, okay. Say it is in nanometer. So, and radius for d1 in say meter. So, from that table you will get, so that, and this for d2 means second ring, for second ring this. Okay. So, from here, so basically lambda versus r, lambda versus say r1 and lambda versus for r2 you can plot graph, and now from that graph that slope will give you r by lambda. Okay, as I mentioned r by lambda, slope will give you r by lambda. So, from this graph you can find out this r by lambda. So, that the slope. So, this is for ring 1 and this is for ring 2, and corresponding you will get d1 and d2. Okay. So, other planes are there, but their angle is basically very high or very small, whatever. So, it is not in this range, it is not in this range. Okay. So, that is why we are seeing this just only two this we are getting this ring for 2, and this also depends on the distance of these two. Okay. So, more can be seen also, but here the distance capital L is fixed, we cannot change. So, that is I think supplied, it is I do not remember, but I think it will be around diameter will be around I think maybe 15 to 20 centimeter. Okay. So, that is the capital L. So, that I think one has to see this manual for this, it is a company supplied. So, one can get basically calculate the value of d1 d2. So, this is very nice experiment. Okay. Just simple cathode CRT cathode ray tube and one screen, spherical screen. This part is I think phosphor material is just put on this part. So, we are able to see the electron position of the electron. Okay. So, here clearly we are getting the diffraction pattern. Okay. So, one has to understand why if we use grating, sometimes you are seeing the lines, you have seen this, we are the lines. So, in this case we are seeing the ring. Okay. Why we are seeing ring, that I tried to explain. Okay. Why it will be concentric ring, and each ring is corresponds to the to a particular plane. So, I think this clearly diffraction, no doubt about it, and this diffraction is basically is visible in a very simple way in the laboratory, and this very compact form, and so all things are known. This we need electron beam, CRT is used, and then we need a screen like CRO. So, this type of arrangement is made, and as a grating we are using some graphite material, okay, in polycrystalline form, so that we do not need to rotate the crystal to vary the angle. Okay. So, these are basically is the using our experience, knowledge from other experiment. So, this experiment easily one can set and demonstrate. So, I think these are experiment is very simple, but is very fundamentally is very important experiment where we can show the diffraction pattern of particle. So, that means particle also have wavelength, and that is what we demonstrated in this from this experiment. Not only that, we also can study the crystal. Okay. We can find out the interplanar distance, d-spacing. If you know the d-spacing, then you can find out lattice constant, okay, because it is the related A, B, C. If it is cubic, A by square root of A square plus K square plus L square, H, K, L are mirror indices, okay. And yes. So, so one can identify the plane also, which plane. Anyway, so more details we are not going to tell you, but just simple way is the how to measure the interplanar spacing using this electron diffraction that we could see from this experiment, as well as the wavelength of the electron beam. It is related with the anode voltage, and exactly for that wavelength one can find out, one can verify through this experiment that this planar spacing d1, d2 whatever we are getting, if you just check with the compare with the literature value, then you will see this is very close to the literature value. That means the wavelength of the electron whatever we are calculating, this is the basically wavelength of this electron, no doubt about it. And I think I will stop here. So, thank you for your attention.